For that. Okay. Your signals and systems and Navin sir has taken morning some class, I think in this board. So he's recording some workbook solutions. So half an hour delay happened. So no problem. So 9:30, now we are going to start sharply now the class. Very good morning. Yes. So today, tomorrow, we'll try to complete the MOSFET DC analysis part. Today, tomorrow, we'll try to complete. Okay. I'm expecting all the students came. So already I have been messaged that my class will be at 9:30. I think most of the students came live. Just 2 minutes is there. Meanwhile, today class, what are the topics we can develop? Let us write the topics. Today class is fit testing and fit passing is today class. So tomorrow class we'll try to see 2 more modules are there. One is on what I can say current mirror techniques tomorrow class, because BJT is not only we designed for current mirrors, MOSFET also we can take as a current mirror techniques. That is tomorrow class. I'll try to complete that module. And then there is one special topic about MOSFET is not only an amplifier, it is a good switch also. In your digital electronics we call this as a CMOS inverter switches. So in our syllabus we have that NMOS inverters, okay, and CMOS inverter technique questions also there. So that module is a separate module I'm going to develop in the class of MOSFET. So tomorrow class we'll try to deal that modules. One is current mirror module, morning class, and one more module we have is very good morning to all of you. One more module we have is what I can say inverter problems. We can say CMOS inverters and NMOS inverters. वो कल class देखते हैं. आज class morning to evening. Let us complete this task. That is called fit passing and fit testing part. But today what is the problem for me to start the class is here electrical students and EC students are watching. EC students already in devices here they have some knowledge on the device called JFET and MOSFET. But this electrical students does not have any idea about that. Without teaching some flavor of EDC, we cannot touch the analog electronics of MOSFET. But in BJT class, in diode class, without the flavor of EDC, we can face the analog electronics. That is the problem. So today, some portion, morning class for about 3 hours, we'll try to understand some issues about the device part, where we have to visualize how the JFET will be, and what are the constants for that, what are the equations, what is the characteristic graph for this. That type of sort of discussion will be there in the morning class. Slowly we'll enter into the afternoon classes with respect to first module is the testing part will be covered, and next part will be biasing part. So this module's syllabus, how to develop, try to see the module, how to take the syllabus. Let us complete the topics like this in order. The topics you can write like this. In chapter 5, we'll cover the subject like this. First point, topic number 1, basics we'll cover first, which will come from the device flavor. Basics of FET. Basics of FET device. In this basics, I covered 2 types of concepts. The first concept is JFET device analysis. I'll give the knowledge about how a JFET device analysis can be done for analog electronics, which comes under the ADC device concept. I'll not take much analysis, a very quick revision I'll go, because electrical students mainly requires analog part with the help of device. So don't waste the time on this. And MOSFET, a flavor of MOSFET device analysis will be there. Who can cover these 2 parts only? You're ready to start the main topics called testing and biasing we can do it. So these 2 topics may take hardly some 3 hours to understand certain equations, graphs, all these issues. We'll try to speak in the class. We cannot take the output from common terminal. Please remember this. Common terminal itself is telling I'm a common point. From a common point, how you take the output? So from the common point, we cannot take the output. Okay? Common points, we never take the output. So the second, after covering these issues, we'll get some grip on the device equations, all the stories. Next, you are ready for the module called FET testing part. How we done in BJT, same thing. Here testing part we are covering, FET testing. In this, how many regions we are going to cover is 4 regions we are covering. One is cutoff region in transistor FET. Second, we are covering ohmic region will come here. These are the operating regions we have. Ohmic region. Next, we will have triode region. Last one, we have current saturation region. So these are the 4 testings how to do in analog electronics. Okay. To understand these concepts better, this device analysis will help us. So the testing part will be easy and comfortable for you. Okay. Each and every method I'll explain you. Cut off how to take the example. And not only today NMOS, PMOS also we have to understand. So this testing may not take much time here. Hardly takes 1 hour class. Okay. But this class will take more time to understand each and every step of equations, all these basic things we have to learn. Most of the students are weak in this concept only. That is called device part. They are very weak. The concepts who learn properly. Analog portion is very easy actually. So this takes only 1 hour class. Okay. Testing part will be completed very soon. And one more we have is concept number 3. That is a FET passing class is there. FET passing. Like BJT passing, we have FET passing classes there. Because for every amplifier, passing is required. So FET is also an amplifier. Majundar, don't say like that. Gate EC may JFET is not there, don't say like that. Okay? Because you don't know, JFET in the depletion MOSFET is the same. If you study depletion MOSFET, JFET is completed. If you study JFET, depletion MOSFET is completed. Both are similar to each other here. So by chance, if they give the parameters with respect to JFET, suppose in the exam, what will do? In the syllabus, they will not mention like that. They will say only FET or MOSFET will tell. But in MOSFET, there is a family called JFET. Okay? You cannot decide yourself that JFET questions they will not ask in gate exams. Common sense use karo. Okay? They will ask. Yeah, whatever I thought till now, they're all in gate syllabus. Okay? JFET also is nothing but depletion MOSFET only. Nothing to explain much about that. So, first point number 1. In this, we have one category called as depletion MOSFET. Depletion MOSFET. In this only we call it as JFET. Common sense use karo. JFET and depletion MOSFET. How can you divide like this in the syllabus? Okay? Both are very important to study the subject because sometimes depletion MOSFET will be given with JFET parameters actually in electronics. Then kya karega? If you don't know JFET in the class, then how will you do this depletion MOSFET problems? So don't think like that. When the sir is teaching means there may be some importance in our subject. Okay? Unnecessarily why I'll teach the classes. So please understand that and how I'm teaching, take the guidance and do it according to that. So depletion MOSFET and JFET. In this biasing we are doing, both are same. Biasing technique will be same. So in this we have 3 types of biasings. One is called fixed bias. Like BJT class, we have fixed bias here also. Next we have is self bias. Cell bias we have seen in BJT class already. RE biasing we call it as cell bias, correct? This is called 2D is called current saturation. 2D we call it as Rajneesh Kumar. It is current saturation we call current saturation. Current saturation. It is called current saturation. And cell bias. And the last biasing we have is voltage divider bias. So these are the three basic biasings we have in depletion MOSFET, or if the question converts into the JFET also, same biasings we can use. So both will have the same biasings. Why they are same, all these issues I speak in my devices. This only most of the students have confusions. All these things I'll avoid with my small explanation for you. So what about the last B point? We have not only depletion, we have enhancement also here. Enhancement, MOSFET, biasing is also there. B point we have is enhancement MOSFET is different, depletion MOSFET is different. In this also we have three types of biasings. One is called fixed bias. The first biasing we call it as fixed biasing. The second bias we have is voltage divider bias we can do. Voltage divider bias. Same popular biasings we have. One is fixed and one is voltage divider bias. One separate biasing is there here. That is drain to gate bias. Drain to gate bias. So these are the certain modules. Who will study properly step by step. Okay, doing the problems in competitive exams is very easy and comfortable. Lack of having some confusions in the equations or notations in MOSFETs, the student will get difficult in solving the problems. Because here, FET is not a single family. It's a family of two, JFET and MOSFET. In the MOSFET also we have four families again. Depletion MOSFET is there, enhancement MOSFET. In that we have N channel, we have P channel. Because of a lot of things, the student will get confused. That's why today my motive is to make all these things in an order for you, like a short notes behavior I'll explain to you. Because for electrical students, the depth is not required. Only that analog EDC syllabus, whatever he has given, that is meant to develop the analog electronics in this class. So how much content you have to study, what parameters you have to remember, what parameters you have to apply, that concepts how to study, I'll try to show you in the class. So don't get confused by yourself as EC students. JFET is not there in the syllabus, don't speak like that. Because JFET, if you don't understand the basic mechanism, okay, MOSFET does not have a meaning pitch. JFET will not take much time. Only it's taking 1 hour to understand the device complete analysis. Okay? Exams they try to give the parameters in terms of JFET also. But JFET parameters are similar to depletion MOSFET. So these all things, lack of this knowledge, you are speaking like that in the classes. Saying that it is not in the syllabus, it is not, they never write in the syllabus. We should use the common sense. Already JFET questions has been asked in EC students previous years. Okay? So you should not speak like that. We know that every year how they'll ask the questions. According to that, I'll frame my syllabus for you. Okay? Unnecessary things I'll not explain. What is required, I'll explain always. So with my experience, I know how they'll ask you. So please believe me and study the subject. So please note on this, some internet connection problem is that just wait for 2 minutes. Meanwhile, please copy these points. So please copy all these things. Today we'll try to start the concept. Okay? So total 3 modules we have to cover. We'll make it as 3 videos. First module I'll cover it as this part today. After that I'll give the break for you. After the break we'll cover the FET testing. That is one module. It will be covered as one video. Part 1, part 2, part 3 like that. This will be one video. 3 videos we have to cover today class. So let us start the class now. So if you are completed, please tell me. We'll start the analysis based on this. First part we are developing some device concepts. Okay? How the device will be. What are the equations? What are the graphs? All the stories I'll explain. And second one, we'll try to see about the testing part. Okay? Lastly, we'll complete the biasing part. This is the order for today class. Tomorrow we'll complete the remaining concepts called inverters and some other things. So by tomorrow we'll finish the total DC analysis of MOSFET. So I think most of the students have completed. Let us start our journey. Great. Great. Radha is telling copying. So please copy it. We'll start the class. Already half an hour has been delayed. Okay then, let us start the class. Let us start our first journey. Keep the heading. Basics of FET device. Keep the heading. Basics of FET device. This is our first class today. Electrical student also should understand now. EC student, everybody should understand. That's why this way of teaching is important now. So basics of FET device. We started with the FET now. What is a FET? We'll see now the story. So first we'll start with topic number 1. Subtopic you can write. Topic 1 is JFET. We are first studying the concept. JFET device. Device analysis we are studying. Just I'll keep some group of points to understand this device. Try to understand the group of points what I'll develop in the class. Keep the heading, separate heading. JFET device analysis. First I'll start with some ideas. Try to understand it. JFET device analysis. Generally, first point, if I write heading, classification first we'll understand. First heading you can keep. First heading is classification of JFET is my first idea for the student. Classification of JFET and symbol, representation. Whenever you enter into the device, first a student should know how to classify the JFET and what is the symbol of JFET. This is the first idea of it. So you can see your JFET. First of all, what is the meaning of JFET? In the abbreviation you can write, it is called junction field effect transistor we call. The abbreviation of JFET, we call it as junction field effect transistor we call. Okay. How it is going to classify is, it is classified into two types there. There are two types of JFET transistors. You can classify it like this nicely. One transistor name is N-channel JFET we call. The first transistor name is N-channel JFET. Another transistor name is P-channel JFET we call. So one is called N-channel JFET, one is called P-channel JFET. Okay. N-channel JFET, how to represent the symbol? If you see, they try to show like this. This is called a representation of JFET symbol. Up to now, BJT symbols we know. Now you can see the JFET symbol. So this is the way how he is representing an N-channel JFET symbol. Okay. Always I'm telling you that arrow wherever you represent in a transistor, there is a diode movement in the device. That movement I'll understand when I teach the block diagram analysis in the next step. So let us keep this point. The arrow will show towards the junction side. This is a junction. Vertical line is a junction to the device. When it is towards the diode is moving towards the junction, we call it as N-channel in this device. And P-channel, if you want JFET, this is drain, this is source, and this is gate. And we have here arrow should be outward. When the arrow is inward, we call it as N-channel. When the arrow is outward, we call it as P-channel in electronics. And what is the notations meaning here? What the indications here? G, S, and D. If you see the indications, you can write the indications here. Your S represents here source nodes, the name of the S symbol. And G, we call it as gate. We have given a terminal name as gate. D for drain, we have given. So this is the way three indications are there. Source, drain, and gate. So this completes my first basic knowledge about the topic 1 in JFET. So first we got an idea that JFET is classified into two types. One is N-channel JFET and one more is P-channel JFET. So how to represent an N-channel, how to represent a P-channel I have shown you. When the arrow is towards the junction, we call it as N-channel JFET. When the arrow is outward to the junction, we call it as P-channel JFET. Okay? It's called P-channel JFET. So what is the meaning of this arrow in the class here is, the trick is here, the concept is very easy. You can see the trick. The diode is contact between gate to source is like this. This is the meaning. Gate to source, the diode is indicated. And here, your diode moment is like this between gate to source. That means there is a P-N junction between gate to source. So this diode moment, it is explaining the arrow indication. If the diode is downward direction, the arrow should be inward, such that this material will become here N material. If the source becomes N material, it is called as N-channel JFET we call in electronics. There is a trick how to remember. This is an N-channel. And your anode is connected means here P-type material is connected to the source. That's why it is called as P-channel JFET. So this is the story about the symbol techniques. Okay? How to recollect? This is a P-channel, this is an N-channel. We come from this trick point. N-channel means if the cathode is connected to the source, we call it as N-channel. If the anode is connected to the source, we call it as P-channel JFETs. Up to here. There is no trouble for you I'm expecting. Up to here. Now the story is, we have two drops in the symbol. You can see. You have two drops in the symbol. Suppose if I take, this is your N-channel. This is your N-channel I have taken. This is gate, source, and drain. This is called N-channel. N-channel JFET. This is called N-channel JFET. So how the drops we can explain here is, VGS will become one drop here in this device, VDS will become one drop. So input drop we try to give the notation as VGS in JFET, and output drop we give the notation as VDS. What about the P channel if I want to know how to write the notation is? For P channel you can represent like this. This is arrow, this drain, this is source, and this is gate. So we have here also he is writing the notation as VGS only, he is writing the notation as VDS only, for P channel also. So in FET devices, he is not changing the notation for N channel or P channel in these classes. So what is the reasons for that? Okay, because of so many families we have here, if you change the notations like that, you will get confused. That's why what he said is the trick. Only remember the signs of the devices. You just always speak whatever may be the MOSFET in FET classes. VGS you write as VGS only. Don't write VST like that. It will confuse your mind. And VDS you write it as VDS only. But in BJT class, we have only two transistors, NP and PNP transistors. But we have so many families in FET devices. That's why we don't want to change the notations. We try to remember the sign techniques. For N channel, how the signs will be, how the P channel signs will be, that we are going to study in the next point. So this is the drops in the class. It may be N or it may be P. My notations will be same. Input drop I'll write VGS, output drop I'll write VDS. Maybe they may be negative or positive according to the mechanism. So please complete up here. The topic 1 is very clear, I'm expecting. Let us see the second subtopic what happens. Idea number 2, I'll explain you what is the next meaning. Try to see. So write down clearly, step by step. It will help me to teach the class in a good manner. The analog electronics will be easier for you if you can understand these points. The first point is classification of JFET and the symbol notations, how to write. So now onwards, the symbols if you want to write, only you write VGS drop for any type of field effect transistor, it may be N or P, you write VGS only the notation, VDS you write as output drop always. Okay? Let us understand the science behind that now, the concept. So let us see the second topic, subheading 2 we'll see. Next is subheading. Next is subheading you write like this. The difference between BJT and JFET. This is very important to understand to start the class. What is the main difference? Difference between BJT and JFET. Where is the difference is coming? Just observe it. For example, we'll take, suppose, NPN transistor I have taken here. In terms of BJT, I have taken an example of NPN transistor. You know how to represent an NPN transistor symbol which we practice in the class? Your transistor symbol will be like this, BJT symbol. This is base, this is emitter, this is collector, correct? So what is our theory is, to operate this transistor in active region, this person is making this as forward bias. Input junction should be forward bias. That means you can write like this otherwise. The input base should be forward bias you have to do, and you keep this point as a common point. You keep this as a common ground emitter. So base is the input which you have to take forward bias, and the rule number 2 is the collector, which is your output, should be reverse bias, such that this device will work in active region. This device will work in active region. This device will work in active region. This is the story which we have studied in the class. Input should be forward bias, output should be reverse bias. So input, if you consider as a base here, the base should be always forward bias, and the collector is output, it should be always reverse bias. This is the story about your BJT. Okay? So base, emitter, collector position, we understood like this. Now the point is, if input is forward bias, input is forward bias and output is reverse bias, I want to know the input impedance from this device. If you calculate the input impedance from this device, if you calculate your ZIN, it will be always low impedance will come. Okay? Low impedance, because input is forward bias. So you get a low impedance will come. Whenever you calculate output impedance from here, which is reverse bias, which is your ZIN out, will get high impedance. Because of reverse bias, we'll get high impedance. Because of forward bias, we'll get low impedance. If you want to calculate the impedances of this device. The same story, if I take for N channel, suppose. N channel JFET. Suppose if I see the comparison between these two devices, what is the difference will come? Carefully understand. This is N channel JFET. The FET device should be shown like this, except. This is a drain, this is source if I make ground. This is gate. So if you see both the devices in the class, this is an NPN, there is an N channel device. In analog electronics, if I want to use both the devices, what are the similarities we can consider? What are the differences we can consider? If you see correctly, the arrow here we have given to the gate point, but here we have given to the emitter point. There is a difference between these 2 points. The arrow, in that case, we have given to the gate, here we have given to the emitter. Is there any equivalent terminals in the class? Is whatever the base you are seeing here the input became the gate for you. So let us indicate this is your input, and this is your output. So in place of base, gate is working as an input here. In place of collector, the drain is working as an output in this device. Okay. But how to operate this device? He's telling is, you will surprise in the class, he's telling that the gate, whatever you are connecting, it should be reverse bias we have to operate. That is a little bit confusion for the students to understand this device part. It's a somewhat a confusion device. This person is telling the input should be reverse bias, not forward bias. So there's a slight difference between your input biasings. Whenever I teach BJT biasings, the input junction I'll make forward bias. Whenever I teach FET biasings, that is called JFET biasing, the input will make reverse bias. So why we will make reverse bias will come in the next explanation called block diagram analysis. Here I'll explain you the content. Here reverse bias is important, always. Have this knowledge. Input should be reverse bias is important. And the drain should be same, it should be always reverse bias. So can you see the surprising point in the class? Your N channel JFET, if you want to work in active region, it has to work input reverse bias, output also reverse bias, then only it can work in active region. So this position, that is reverse bias, we call in BJT class it as a cutoff position in electronics. But this is not in cutoff, it is in active region when you operate like this. That is the specialty of a new peculiar device in electronics called JFET. JFET is somewhat peculiar in nature. The peculiarity I'll explain. So we can see here, the input impedance, if anybody asks you, will say this as high. Always JFET will say high input impedance, because you have been taken reverse bias, not forward bias in the class. And output impedance here, output impedance will also be high in this device. That's why both the devices are slightly different in the impedance behavior. You can see the input impedance of BJT is low, but the field effect transistor input impedance is high because of the reverse bias mechanism what you applied. And output is reverse bias, both will have the same impedance nature. High impedance, that is also high impedance. These are the very, very common things a student should learn before entering to the analog IC design parts. Okay, integrated circuits if you want, you should be very careful to observe these points. So this is about the differences. And is there any common things in the class? Is there any common things? Means yes, the base of this transistor BJT, the base of this transistor will be equivalent to here gate. That means whatever the base will do the work today, common base transistors will say, the same work our gate will do the work. That's why who will say common base amplifiers? What are the applications we use in analog electronics? The common gate amplifier will also do the same application. So now onwards, base is an equivalent form of gate of your field effect transistor. Okay, base is an equivalent type of base. Okay. So next we'll see another equivalent value is emitter. If you see here in BJT, emitter E, the equivalent for this is, you can have an equivalent nature. Here is source we call. So source is an equivalent form of emitter. So in analog electronics, that's why a common emitter amplifier and a common source amplifier will perform in the same manner. Whatever the applications you have for common emitter, the same applications will come for common source amplifiers in the next classes. So the source can be equivalent to the emitter. Gate will be equivalent to the base. Okay. And last we have one more. That is collector. In BJT class, whatever collector we have, that is equivalent to drain here. That is equivalent to drain. So a student should have this knowledge first. So these are called equivalent terminal parts we can say. These are the equivalent terminals, but the story is base we have to apply forward bias, but gate we have to apply reverse bias. That is the difference in the BJT and your JFET electronics. Okay. Up to here, if you can understand the story, similarities and the differences, we can start thinking what is an N-channel JFET, how it looks. That block diagram analysis will understand, and why input should be reverse bias, why output should be reverse bias. If you can explain that point, I'm successful in understanding the JFET device today. Okay. So let's see this story in the next point. That is topic number 3. One by one, I'm explaining the step-by-step procedures. So keep the heading next one after this. Yes, collector is equivalent to the drain. Very good. Emitter will be equivalent to the source, and base will be equivalent to the gate. I think electrical students, I think you are following my class. Mainly for electrical, this is a very tough job for me to teach at this level. So in a sequence manner, I'm teaching so that you'll understand very clearly the concept. EC students already have some knowledge about this device, so they can easily understand what I'm teaching. Electrical students also please try to grasp the concept what I'm teaching them. So up to here, no toughness I think is tough here. So differences in BJT, base is forward bias, and in FET, gate is reverse bias. Yes, Arpita, perfect. Those statements go through my mirror. Great. So this completes the differences in the concept. Common drain amplifier also present. Yes, shall we differently? We have common drain also. Okay. Common drain is equivalent to common collector. Yeah. If you complete these points, we'll just move to the next slide, which is the main concept now. Keep the heading. Keep the heading here. Next concept. Block diagram. Block diagram. Keep the heading. Block diagram. Block diagram of N channel JFET. Block diagram of N channel JFET. Let us see the idea of block diagram. This is the main important visualization we want. Block diagram of N channel JFET. So how he is going to design JFET you can see. First he is going to take one material like this. It's not a big construction, very easy construction. BJT is a complicated, but FET you can enjoy it. So he has taken one material like this nicely. But that material is a semiconductor material. We have two types of materials in our life. One is N material, one is P material. Most of the students know that. It can be N or it can be P. N type is being doped with pentavalent impurities, correct? 50 group elements we are adding. And P type is being doped with the, what you can say, trivalent impurities. This any material you can take, choice. Okay? Let us take with this material as N I have taken. This is an N bar, I can say, semiconductor bar. If I take this as an N bar, complete bar, I'm giving two terminals here. Here, one terminal, which is called source, I'm giving this side. And here, I'm giving one more terminal called as drain. So if you correctly see, in a single material, one end I have given drain, one end I have given source. In exam point of view, there is one theory question in ESC syllabus I've seen most of the times. Which device in electronics, where you can change the input terminal and output terminal interchangeable, is asking. If you see in the JFET device, source is connected to N, drain is also connected to N, same material it is. But in BJT class, it is not like that. Emitter is heavily doped, where emitter is connected. Collector, we have taken lightly doped, where it is connected to the collector side. So emitter, collector have different doping levels, so you cannot interchange like that. That game you cannot play in BJT class, but that game you can play in field effect transistors. So source, drain, you can interchange. In JFETs also we can do that, in MOSFETs also we can do that. That's why FET family have this different technique. Source and drain, whatever you want, you can change in the lab. It will work out. Okay? So source and drain are interchangeable here. That is one important point you can learn from this board. Source and drain are interchangeable. Source and drain is interchangeable. So next point. If I want to gate, what I'm doing is, some part of the material I want to dope with P-type material. And on the other side also, I want to dope with P material. So there is one rule in the class. When you're doping with some other material, some portion in your N material, there is a concept called in semiconductor electronics called compensated semiconductors, we call this as. What do you mean by compensated is, suppose this is my N material in the class. Some portion, I want to make it behave like a P-type. Then what you have to do, here you have to dope more number of holes compared to the electrons in that area. If you dope more number of holes, it looks like a P-type material. That is the reason why, when you want to dope some material, in the overall material of N, you should not dope with P like this. Having equal doping is wrong. You always take some extra doping, which will dominate the N material, which will behave like a P material. This is the rule of compensated semiconductors we call in semiconductor devices. Always when you add a new material in the original material, the doping should be higher than the previous material. Then only that will behave as a P material in the devices. That's a very common rule. Please try to keep this in point. Okay? In any material, if you add some other material, the doping should be more than that. Otherwise, it will not behave as a P-type material in the device. That's why P plus means it is somewhat heavily doped compared to the N material. This is one principle which we use in electronic devices. Okay? That is the main reason why I kept P plus there. P plus means it is heavily doped than N material in the class. So this is the structure which we prepared. Because of PN junction, we'll have some depletion region will form like this. In open circuit, we'll have some depletion region. Every student knows that there will be some depletion region will form. So this is called a depletion region. Now the point is, I'm connecting this side with a gate terminal. This is connected with a gate. So these are the three terminals we have. Gate, drain and source you can see in the device. So electrical students, try to visualize the diagram now. This is your JFET construction, which is one of the easiest construction in analog electronics. Hardly I have taken one N material. On the other side I have used it with P plus total materials, which will become a P materials there. So PN junctions will form, so depletion region will form. This is about the device structure. This is called device structure. Now sir, why input should be reverse? Why output should be reverse? That knowledge I have to explain. Can you tell me from gate to source, are you seeing a diode here? Previously, I have represented a diode. This is your diode. This is the arrow I have been kept. Gate to source, there is a type, PN junction diode. This should be reverse bias is asking. We have a talent how to make a diode reverse bias. It's not a big job. How to make reverse bias means, anode should be, this is anode, this is cathode. Anode should be negative, we have to apply. Anode should be negative, cathode should be positive, which will become reverse bias. This is your VGS voltage. Completed. You know PN junction diode knowledge, that only applied. Your diode is reverse bias here, that you apply. VGS, polarity has been came into picture. And same thing, drain should be reverse bias is asking. What is the drain concept here is? You take here one diode again, from here to here. Always you take like a diode representations to understand better the concepts. You take this as anode, this as cathode. You want to make cathode reverse bias. You want to make here reverse. Cathode should become reverse. Therefore, the drain has to be positive. Then the diode will become reverse. So this is the way of understanding the simple way of JFET devices. So this is called your VDS. So I got a beautiful concept in the class. A beautiful analysis. Nothing to think much about the theory. Just ideas are important for my class today. So this is your reverse bias, this is your reverse bias. So drain and gate are reverse bias in the class. Drain and gate are reverse bias. Beautifully I made reverse bias. Now by seeing this device, can you tell me what is the reason of VGS you are applying and what is the reason of VDS you are applying? I'm trying to analyze the concept you can see. So first point, VGS is reverse bias. VGS is reverse bias to control the N channel, with depletion with mechanism. So this is the main secret actually. VGS, why I'm applying in the class here is, you created here some channel here. You can observe there's a path between these electrons actually from source. Actually my intention is, in this material, these electrons want to move from here to here. This is my intention. Where to get some current, the electrons has to move from source to drain. There's a path you created here. There's a path here. You can see a path here, correct? There is a path here. This is called N channel, you can say. You created a channel here. This is called N channel. So that the electrons can move from source to drain nicely like this. Okay? N channel we created. But the N channel, who will control it? If this channel, who will control it? The current will vary here. So to control the output current nature, input has to be control your channel. That means a VGS is reverse bias. Why I have done that reason is to control the channel, N channel. So how you will control means, there is a mechanism called as a depletion with mechanism. What do you mean by depletion with mechanism? From diode theory, according to the diode, reverse bias theory, if you apply reverse bias theory, what the diode reverse bias theory explains for us is, diode reverse bias theory explains us as the reverse bias voltage. This is called reverse voltage. Reverse voltage increases. If you apply more and more reverse bias voltage in diode theory, it is telling that the WB, which is called width of the depletion region, width of depletion will also increases. This is the theory of reverse bias. So what you want to tell is, whenever reverse bias voltage if you increase more and more, the depletion width also increases. But in forward bias it will decrease, in reverse bias it will increase. This basic point a student should learn, as an electrical student I'm telling. So as the reverse bias voltage increases, the width of the depletion region increases. Why it will increase, all these things I'll teach in the semiconductor device. Your only idea is important. So with this knowledge, can you tell how your VGS can control the channel here? Can control the channel. You can see that this is your depletion region. This is your depletion region. This side also we have the depletion region. Both sides we have depletion region. You can have both sides depletion region. And please remember, this side also we have the gate, but most of the times we don't show both sides actually, because this is interconnected again here also with negative, positive. So both sides not required to show because both are interconnected inside. That's why one side if you control, other side also will happen same. So if you want, you can have a clarity like this. Both are connected to same VGS pattern on both sides. Okay. So keep some point in mind. So as reverse bias voltage increases, base voltage will increase. Here reverse bias voltage, according to JFET, if you see the JFET theory now, JFET theory, according to this knowledge, what happened is, reverse bias voltage means here VGS, you are increasing. VR is increasing means in JFET, VGS is increasing. So there are diodes wise we say VR, in JFET we say VGS. Both are called reverse bias voltages. As the reverse bias voltage increases, your width of the depletion region will increase. So that means this width is going to elongate like this. It will expand it. If the depletion region increases, have you seen that your channel is decreasing here? As the depletion region is increasing here like this, the channel will get decreasing here. So that means the channel can be controlled with the width of the depletion region. So N channel, we can write here, your N channel will get decreases. So this is the mechanism which we are doing. So to control the N channel in the class, we have applied VGS as reverse bias voltage. It is not for current, it is only for control of the channel. So as VGS increases, WB increases, your N channel will get decreases. We are not increasing, we are decreasing actually. Okay? We are decreasing. That means what I can understand is, at VGS equal to 0 volts, that means if you don't apply any reverse bias in JFET theory, you will see the maximum N channel. Maximum N channel will be there. This is a very important point. So you can see the maximum channel when you don't apply any reverse voltage. But when you start applying reverse voltage, that N channel will get decreased. So up to here, if you can understand clearly, next point I'll try to make it develop in the class now. Step by step, you have to get the mind with this concept. Visual that S as equipotential meaning this point and this point, if it is a common for both sides, it is called equipotential. Here equipotential label, it's a common point for the gate and the drain. I'm talking in the class. Okay? I'm not talking all these equipotentials, all these issues. Maybe with respect to gate on both sides, it is equipotential for source. Okay? So, Pawan Kumar, thoda wait karo. VDS I have not started my explanation. Be happy up to here, the class. Next point I'll explain slowly about VDS now. Up to now, VDS story, please keep in mind. Don't forget this point by asking some other question. Okay? I'll teach each and every point. Let us understand this theory as an electrical student mainly. I'm focusing for electrical student mainly. VGS is reverse bias. Why anybody asks you? It's a simple meaning to control the N channel. How you are controlling the N channel means, as the reverse bias voltage you are increasing more and more, the width of the depletion region also increases. As the width increases, the channel will get decreases. At VGS equal to 0 volts, anybody asks you how much is the channel you are providing for me, you have to say maximum channel will be there at 0 volts. Okay? This is the story, first try to understand it. Concept number 1. Pandit, what you बोल रहा हूँ यार? VGS equal to 0 means we have not applied any bias voltage here. We have not applied any reverse bias voltage. At the time, manufacturer has given this much channel for me. Manufacturer has given that much channel. But when you apply a reverse bias voltage, -1, -2 like that, the width is increasing and the channel is decreasing there. That means can expect if you don't do any bias, you will have the maximum channel he is telling. Initially you have maximum, but when you are operating it, it is becoming minimum. That is the meaning he is telling. Yes, Akshat. VGS is internally connected, so every time it is not required to show you this gate terminal. Okay, for study purpose I'm showing you. So let us see next point. Same slide. I'll explain you the second point. Second point. So what is the next point you have to understand is point number 2 here is VDS is reverse bias. Why? This question will come to you. VDS is reverse bias to send the electrons from source to drain. Send the electrons from source to drain such that drift current ID will be produced. So this is the concept of VDS. So Panjira, what you are saying is correct only. Maximum channel is required actually, but a device thoda peculiarly behave karega. So don't get confused. Okay, it works as a peculiar device. That's why it has certain more drawbacks. That's why we have gone to MOSFET families. Okay, there is some reasons why we are moving to MOSFETs. Okay, so this is the second point. Very clearly I have written the board. Please note on it. VDS is reverse bias. Nothing is there to send the electrons from source to drain. We want to inject the electrons to move from source to drain. We apply VDS. Why sir drain became reverse bias in the class is? It's a very simple logic which is called drain current, which is called drift current. You can see here this is source. Electrons has to move from source to drain is important. The source, if I connect a negative battery, negative and negative will get repelled so that the drift current will start. Electrons will move in the channel like this up to the drain. When drain is connected to positive, the electrons will attract to the drain side. So that is the reason always the drain should have a positive terminal so that it will attract the electrons where the source will repel the electrons. That is the mechanism. Okay, that's why automatically what happened, drain became reverse bias because it has to attract the electrons. Therefore, N region we have connect positive, automatically the drain will become reverse bias to give the drift current ID. So you can get a ID current here in the class. You can get a ID current here. So can you see the ID current flow direction will be downward in the class. As electrons are moving upward, the direction of the current will be downward. Your electrons are moving from source to drain. Electrons are moving from source to drain. This is your electrons are moving like this in the channel. So the source I said that connect negative polarity, drain please connect positive polarity like this. This is the mechanism. As the electrons are moving due to the drift concept, electric field you applied, I think the current flow direction will be like this we have to show. This is the moment of current. This is your ID current flow direction. It's very easy to understand this type of devices. Your current will be always shown conventionally opposite to the movement of electrons. So this is the story here. So ion Roy, source is connected as a positive, correct only. Source is connected as positive, but here we have to speak about input terminal, output terminal, not about the common terminal. Common terminal, it may be positive or negative to DJ. We are interested, gate how it is connected, drain how it is connected is important. Unnecessarily don't think about the source, okay? Our interest is about output and input, not the common point. If suppose drain is positive, compulsory source will be negative one, common sense it is. Okay, don't think about source. Talk about drain point and gate point, how you connected is important. So what is the meaning of a drift current? In coming classes I'll explain you, it's a simple thing. The movement of electrons due to the electric field, we call it as drift current. Okay? We are getting to the electric field, the electrons are moving there, that we call it as drift current. If you want, I can write here the movement of electrons due to electric field. The movement of electrons due to electric field is called as drift current. Not more than in your class. Whenever you use electric field mechanism, the current flow we call it as drift currents we call in electronics. Yes, Jahnavi, what you said is correct. Source side we will apply more negative, drain side we will apply more positive, electrons will repel from the source, you will get more current. That means you have to apply more VDS voltage such that you will get more and more current in the devices. Okay, VDS is meant for to get the drift current. How much VDS you apply, more and more electric field, you will get more and more current for in the devices. Okay, so this is about the story about first topic and second point. Up to here, I'm expecting this device is clear, concept is very clear. The only thing is the notation signs are important here. That is the final step you have to understand. As the space is not there, after that I'm writing point number 3 here. Notation signs are important. Last point is your VGS notation, we have to take it as negative in N channel. Your VDS, we have to take it as positive. These rules are for N channel GFETs. So whenever you are representing VGS value in N channel GFETs, that value is considered to be a negative battery and VDS should be a positive battery. If you see the battery position, this is plus minus positive battery, and if you see this is a positive negative battery, so VDS will be positive always for N channel. VGS, gate is connected to negative, so VGS will be always negative. Like that, understand and remember the sign techniques. N channel, VGS will be negative always, VDS will be positive. If you have any doubt, you just write the polarity technique like this and you just throw the signs to the person. Okay? So this is the complete story of my beautiful concept. N channel GFET visualization I have done in the class. N channel GFET, how to visualize is the concept. So please complete it. The same thing, I'll show you P channel story in the similar manner. Copy these 3 points. Hardly 3 points I explain, not more than in this concept. This is first point here, it is very clear. This is second point, very clear. This is my last point. From the diagram is most clear in the class. These 3 points is my visualization about this device. So complete this story. Yes, Pandit. Increasing the VDS will increase the drift current. So you can write here otherwise. You can add this point. As VDS increases, your drift current ID also increases. If you want, you can add that point. As VDS increases, ID also will increase. Up to here, I'm feeling happy to show you the content like this. Very beautifully, you can understand this content. Electrical students, mainly, I hope you understood the visualization of N-channel GFET, how to understand it, device part. Okay? What is the reason behind input reverse Q Carrevo, output reverse why he is doing a beautiful explanation in the board for you. Why should I do like this? That means gate to source is not responsible to give the current. Drain to source is a responsibility to give the Yes, Shabnedas, yes, correct. ID always will be opposite to the flow of electrons. Okay. VDS is more than n channel decreases, then how drift current will increases. Right? Up to some time it will increase. After some time, some consequences will come. That story I'll teach in the graph now. Don't worry. First, in initial case, as VDS increases, ID will increase. As electric field increases, go on increases. At the time, behavior will change. I'm telling you, first initial case, as VDS increases, ID will increase. Okay. And this condition is good for small VDS values, not for large VDS values. This condition is good for small VDS values. This is good for small VDS. If you want, you can write it. If you go for large VDS, it will change again. Yes, sir. Divyadas, what you said statement is wonderful, correct. We need less VGS, we need more VDS to give the high current. Pooja, yes, VGS can affect the drain current. I'll explain in the next step. Don't worry. So let us move to the block diagram of P channel now. Next concept is block diagram of P channel JFET. Keep the heading block diagram of P channel JFET. So what is the difference you can see in P channel? Here also we are taking a bar, semiconductor bar, but the story here is, in place of N, we'll take it as P material. And the source and drain, we can interchange if you want. We can interchange the source and drain. And we have opposite material I'm keeping here, which is now N, but it should be heavily doped. N plus we have to keep, and here also we have to keep N plus. We'll have some depletion region will form with certain width. This is some depletion region. And it will create some channel here. This is the channel we got. This is called P channel. We got a P channel. This is a P channel. We created a P channel in the device. What do you mean by P channel is? Now the point is the holes has to move from source to drain like this. The holes has to move from source to drain. Now what is the polarities we can give here is, keep the diode movements. One diode is like this. Another diode is pointed like this. To explain the polarity, write two diode positions like this. And this is anode and this is cathode. This is anode and this will be cathode. So this is your gate. Now it has to become reverse bias. So cathode has to give positive, no. Anode has to give negative. So this becomes VGS voltage. You can see the technique. Cathode should be positive. And here anode should become negative to make it reverse bias. So can you see the polarities has been changed? This became VDS. This became VGS. So VGS is looking positive now. In P channel, VDS is looking negative here. VGS is looking negative. So like this, just you have to remember the polarities of VDS and VGS according to the N channel or P channel. This will be helping a lot in analog electronics, the sign techniques. We're not changing the notations, we're changing the signs. Okay? The VGS becomes positive in P channel and VDS will become negative here. So let us write the theory points based on this. The first point is, same story you can write. First point is, VGS is reverse bias to control the P channel, with depletion with mechanism. Same story, but we are controlling here P channel, not N channel. Okay? Shivam Kumar, what is the notations I missed? Notations, what do you mean by notations here? Everything I have written, so maybe notations will be the third point I write there. Third point I'll write notations, don't worry. VGS is reverse bias to control the N-P channel with the depletion width mechanism. What it's telling is, as VGS increases, reverse bias voltage increases, your width of the base, width of the depletion region, the width of the depletion region, WB means width of the depletion region will increase. Therefore, your P channel will decrease. This is the mechanism. As VGS equal to 0, we have maximum P channel. We have maximum P channel in the device. We have maximum P channel whenever VGS equal to 0 volts. This is the first point. Second point is, VDS is reverse bias. Why we made VDS reverse bias is, VDS is reverse bias. What is that? VDS is reverse bias to send holes from source to drain, such that drift current ID will produce. So as VDS increases, your ID will increase for small VDS values. Here drain is there, here source. The holes are moving from drain to source to drain. So this will be connected to positive is better. This is connected to negative is better because holes will repel with positive. And the current flow direction, you can see the current flow direction will be like this. This is the current flow direction. This is your ID current in this device. So the only difference in the current flow direction is, for electrons when they are moving from source to drain, the current direction I've shown you top to bottom. But for holes, the current direction should be parallel we have to take. That is the difference. Because holes are considered to be positively charged particles, so that the current direction and the hole movement will be always same. As well, the direction of current will go upward now in P channel devices. All the things I covered. Only one issue is point number 3. Notation signs you can see. One is VGS notation should be positive we have to take, and VDS notation we have to take it as negative we have to take. So this completes the total. Sorry, yeah, correct. This is my notation techniques. With this I completed successfully the device basic meaning I completed. Now I'll show you what is the behavior of your current nature with my device. That I'll be showing with my graphical knowledge. Okay. So please complete up here. This is called visualization. How the device devices will behave with respect to two batteries. One is VGS and one is VDS batteries. So you should not get any doubt after seeing these points clearly. Maybe content is not completed, some more analysis I'll teach you, don't worry. Up to here it is, if you understood, okay, further doubts don't ask me because further points I've explained. Just only the meaning I explained about the device at this point. Some more analysis I have to teach you. I'll take some water, please complete meanwhile. So till now we got the knowledge about what is n-channel device, how it is going to construction we have understood, and how the polarities of VGS and VDS. Till now we have been clear up to here our mindset. Let us see the next moment what will happen. We are coming close to the concept, don't worry, analysis is nearly to complete now. These devices are not much tough to explain or to understand the devices, but BJT is very complicated. It requires total semiconductor device analysis. That's why I not explained it. At the end, electrical students will enjoy a lot when I teach the BJT device analysis. Okay? I'm promising you, I'll teach the device at the end of the concept. So that chapter 3 and chapter 1 you can complete with the last two topics, we can complete at the end of the classes. Okay? Showing the direction of ID in the previous topic is downward direction. When the electrons are moving upward direction, the current direction we have to take downward. This is the previous slide. Okay? So the next point we'll try to develop concept number 4. Next subtopic you can keep the heading. Graphical knowledge will understand now the concept. Okay? Graphical knowledge will understand. Keep the heading. Next one. Next subheading. Next subheading. Drain and transfer characteristics. Drain and transfer characteristics. Drain and transfer characteristics. Keep the heading. Drain and transfer characteristics of the effect. This is very important to visualize from the construction point of view. Very, very important for my low classes, so be careful to understand the total graphs now. We have been observed that for n-channel JFET, if you want to draw the graphs, that is output graph and transfer graph, the only thing you have to keep in mind is your VGS should be negative and VDS should be positive we have to take. So let us take this technique like this. So the graph will come both edit and no, transfer characteristics and output characteristics. You can write VDS as positive here, and ID is y-axis you take, and VGS you take it as negative value. VGS is negative. This is positive, this is negative, this is in milliamperes. So if you see the graph, JFET study graph, we can do two graphs at a time in study. VDS generally we take positive values according to the sign technique, and VGS we take negatives on the second quadrant. ID is a function of both the voltages. Input voltage to ID we can study, output voltage to ID we can study, because ID can be controlled by both the things. Your input VGS also can control, and VDS also can control. So how the graph is coming, just we'll understand the graph. Okay? In the graph you can see, the study graphs are coming like this. This current we call it as IDSS. So the next graph is coming like this. The next graph is coming like this. So this is called VGS equal to 0 volts. This is VGS equal to minus 1 volt. VGS equal to minus 2 volts like this. But transfer characteristics if you see, it is coming like a parabola. This is called some pinch off voltage. This is called a pinch off voltage. So if you take this value as VGS equal to minus 3 volts, it is 0 volts, it is minus 1, it is minus 2, and it is minus 3 volts. So this is the way I have taken the graphs. So this completes the story of your n-channel JFET. Now we have some pinch off voltage here as 3 volts. So take this graph. In a similar manner, if I go for p-channel JFET, your VGS, whatever you take VGS, it should be positive, and VDS, it should be negative. So VGS should be positive, VDS will be negative. See the graph, how to present for this. Here VDS will be negative, here VGS will be positive. This is your ID in milliamperes. Now the graph will come in the reverse manner like this. This is IDSS, this is VP, this is VGS equal to 0 volts, plus 1, plus 2, plus 3. Here we have the current flow like this. This is your pinch off voltage. This is 0, 1, this is 2, this is 3 volts. So can you see the story of the graphs? How the graphs are coming, just visualize the graphs. The same study graphs, we are seeing just like a mirror image in the opposite manner. Okay? Because we are studying the polarities in opposite manner there. So one is for n-channel, one is for p-channel. Yes, Pandit, that only I'll explain you. Please give me the time for it. How the current will decrease, we have to see now. If you see here, the current is decreasing actually as the VGS is increasing. In reverse bias, minus 1, minus 2, minus 3, the current is decreasing like this. The behavior I'll explain you. And this current IDSS, we are seeing the maximum current in the boat. And there is some pinch off voltages in the boat. These points I'll explain you in the concept. We call this as pinch off voltages. Pinch off voltage we call this as. This is called pinch off voltage. We'll get both sides, pinch off voltage. this answer will be minus 3 volts. This is called pinch off voltage. Pinch off voltage. There is a meaning there, pinch off voltage. So Panja and Satya Prakash, what do you mean by IDSS? I'll explain you, don't worry. I'll take 3 points, one by one I'll explain. Give me some time for that. First note on these two things. That new things I'll explain you, what is the meaning of that. That is my job, so don't worry about that. IDSS means what? Clearly I'll explain you what is the meaning of that and what is the meaning of pinch off voltage. These two are very important for this lecture today. What is IDSS and what is pinch off voltage? These two things I'll explain you, don't worry. First complete the graphs for the two devices. For N channel and P channel, how to understand the graphs. If you are completed, please tell me. I'll explain you the meaning of what is IDSS now and what is the meaning of pinch off voltage. These two things I'll cover in the class now. And I think the graph, when you see, you'll get a feeling on the concept that the current is decreasing. You can see the current is decreasing with respect to reverse bias voltage. As the VGS is increasing more and more, I think the depletion will increase, the channel will decrease such that the current will decrease. That's the simple meaning from the graph. Okay? Currents always decreases, not increases. Currents always decreases in these devices rather than increases. That's why these devices we call indirectly as depletion type devices. Depletion means they will decrease with the operation. If anything is increasing with the operation, we call enhancement. BJT is an enhancement device, but JFET is a depletion device. It will just reduce the current. It will not increase the current in the operation. Okay, Arpita, I'm waiting. Please note on it first. Please complete it. So I'm expecting it is completed. Okay? It's completed, everybody? Shavanidas, थोड़ा wait करो यार. Graph कैसे आया वो explain करूँगा ना, थोड़ा time दो मेरे को. First graph लिखकर explain कर रहा हूँ my concept को. So don't worry. So let us understand in the next slide the meaning of these graph points. So you can write below that what is IDSS story. IDSS. You can write the meaning of this is shorted gate drain current we call this as. Shorted gate drain current. What is the meaning of this is? This current is being coming when you are keeping VGS equal to 0 volts. We are getting this current. Shorted gate means you just shorted your gate to source. So what is the definition you can write is? It is the maximum ID value. It is the maximum ID value at VGS equal to 0 volts. And this value will be specified by the designer. So you don't worry about this value. IDSS, we should not worry about this because every field effect transistor, the designer or the manufacturer will throw that value to the user. So in the exam point of view, this IDSS data, they try to give for maximum value. But we are operating below that value, we are not operating above that value. That is the maximum value. Your designer will decide at VGS equal to 0 volts. Okay? Chalo then, second point. What is the meaning now? Happens is, as VGS, whatever you are applying, is increasing reverse bias voltage, as VGS is increasing, what is happening here is, your width of depletion region, will increase. This is the known fact for us. Width of the depletion will increase. Then automatically the channel, it can be N channel or P channel, will decrease. Your N channel or P channel, it will decrease. If the channel decreases, the current flow will decrease. So this is the mechanism, what we are seeing in our graphs. Okay, in our graph what you are seeing is this story. As VGS increases, the width of the depletion region is increasing, such that the channel will decrease, such that the ID current will decrease. This only you can see in the previous slide. This only we are seeing the current is decreasing from maximum to minimum. The current is decreasing. Here also you can see in N channel also same thing. As VGS is applying more and more reverse bias, the IDSS current is decreasing towards 0. So this is the graph meaning in the class. Okay, this is the graph meaning. So maximum you will get at 0 volts, minimum you will get at minus 3 volts. According to this experiment, minus 3 is becoming your pinch off voltage. Okay, minus 3 is becoming your pinch off voltage. So current will decrease with respect to VGS value. So let us go to the second one, meaning point number 2. Second point. This is considered to be first point you take. Point number 1 from the graph. Second point is VB. VB refers to pinch off voltage. VB refers to pinch off voltage. VB is referring to pinch off voltage in the class. When to decide pinch off voltage means it is the maximum reverse bias voltage VGS. It is the maximum reverse bias voltage VGS at which drain current ID becomes zero. This is one way of writing definition. It is the maximum reverse bias voltage at which the drain current ID becomes 0, or another way of writing the same definition again. It is the minimum VDS voltage at which drain current ID will be saturated. So some people will get confused about these definitions. Try to see this and that, both are telling same information to me. Okay. So it is the maximum reverse bias voltage at which the drain current ID becomes zero. This is telling. Okay. And this is telling. If you want to understand that, you can have a rough graph here. You can have a graph. This is VGS. This is ID. You have a graph like this. This is your pinch off voltage, and you have a graph like this. And we have a pinch off voltage here also. So suppose this is plus 3 volts. This is minus 3 volts. So you can see two styles of definitions. One side is VGS, one side is VDS. Suppose you want to define your pinch of voltage in the drain characteristics. This is called transfer study graph. This is called transfer graph. This is called transfer graph. This is called drain characteristics. This is called drain graph, I can say. So we have two graphs, two definitions. Anything is correct now. If I want to define in this region, it is the maximum reverse bias voltage, which is minus 3. It is the maximum reverse bias voltage at which the drain current ID becomes 0. Here if you reach, the current will become 0 because the total channel will get closed off. Okay, as VGS is minus 3, the designer said minus 3, the total penetration will close the channel. Means you are coming very close to narrow the channel so that the ID current will become 0 for you. So that pinch of voltage will not be decided by you or me. Again, designer will decide that value. So pinch of voltage is not my decision. Suppose you want to explain here the pinch of voltage with respect to VDS voltage, there also you can define, but style is different. It is not the maximum, it is the minimum. Because after this you have the maximum values. So VDS when you have to talk minimum. When you talk VGS, you have to talk maximum. It is the minimum VDS voltage. It is the minimum VDS voltage at which your drain current will get saturated. Okay, when you reach to that voltage, a VDS value, your electric field is maximum you applied, so that the current will get saturated. It will not increase, it will get saturated. Okay. So anyway you can explain it. But in exam point of view, which pinch off is better, sir? Examiner will do plus 3 or minus 3 means you can see the correct way of representation now. In exams, generally they try to give data like this. This is N channel suppose. This is N channel. Examiner will give the data like this. IDSS is suppose 10 milliamperes. Pinch off voltage is minus 3. This is the way they will give the information. So I have seen that he has not given plus 3, he has given minus 3 there. So what is the meaning of that? Plus 3 he has given, sorry, plus 3 he has not given, minus 3 he has given because at plus 3, how much the current is saturated maximum? He has given already the value, IDSS. Then what is the meaning of talking about pinch off at plus 3? But here, when you reach to minus 3, the current will become 0, that I know. That's why you have to tell at what voltage the switch will get off. That means indirectly, these two telling about the switch on, switch off conditions in our class. Okay? IDSS equal to 10 milliamps means it's a switch on current we say in our device. VB equal to minus 3 means the switch is getting off there. That's called switch on, switch off conditions. So you can say that at this point, your switch is off. If you use like a switch, the switch can be off here. And at this point, your switch will be on. This is the switch on, switch off behavior of JFET. At 0 volts, it will be switch on. At minus 3, it will be switch off. So what is the actual definition of pinch off then? If you have a confusion, what the designer said to me is, he has given a simple definition like this, a generalized definition. He said that don't confuse with VDS and VGS. Generalized he said is, pinch off voltage is a modulus of VGS plus modulus of VDS. We just calculate the pinch off he said. So we just calculate pinch off with this modulus technique. How much VGS you are applying, how much VDS you are applying, just take a modulus, we'll get the pinch off voltage there. Suppose you said this answer is minus 3 suppose in the class. Okay? Minus 3 you can cut into two parts. Suppose VDS is 1, VGS is 2, 2 plus 1 is 3. You can take like that. Here to source voltage 2 level, VDS 1 level, total will be 3. You can take VDS 2, VGS 1, you will get pinch off voltage. Like the different batteries you can apply, the pinch off voltage will be fixed like that. Pinch off voltage will not change, but you can change these batteries. With the input battery if you are increasing, your VDS battery has to decrease. If VDS is increasing, your VGS has to decrease. Finally the pinch off should be constant. So what is this pinch off, sir, and what factors it depends? Means there is a formula for pinch off voltage in electronic devices. Vp is equal to A square Q times Nd by 2 epsilon naught epsilon r. This is for N channel. You take this formula and Vp is equal to A square Q Na by 2 epsilon naught epsilon r. This is the formula for P channel. So these are the two formulas you just take up. So that means pinch off voltage is not depending on the batteries actually. It is depending on some dimension called A in your device. A is nothing but the channel height he has taken between P plus and P plus. There is some channel. They have taken some dimension as 2A. And if you take half of the material, we say A. You call half channel height. We call this is it's a dimensional value. Q is the charge. Nd is called doping concentration. That means pinch off voltage will not depend on on your material. Sorry, on your batteries. It depends on the doping concentration. If you take Nd, it is an N channel. It is Nd donor concentration. It's a P channel. It is Nd. It is entirely depending on the channel doping. Okay, that is the reason. These values we should not calculate. The doping how much the designer added, he knows. I don't know. That's why these formulas will help you to solve certain 1 mark questions for you. So take the formulas. What is A here? I'll write. What is A? What is the meaning of A? I'll explain. See here. Suppose if your device is like this, JFET. This is your JFET. Horizontally I'm showing. This is gate. Sorry. This is source. This is drain. This is gate. This is gate. You have some P plus. You have some P plus like this. Like this you have the device. He has taken here half of the device. If you cut like this becomes half of the device. Two PN junction devices you can cut like this. The total area, the total channel height he has taken as 2A. This is 2A. Then half channel is A. So this is the dimension. 2A means full channel height. A means half channel height. So 2A decides full channel height we call. And A is called half channel height. Just that formula you can practice it. And Nd is called as donor concentration, which is the N channel concentration, N channel doping concentration. And Na is called acceptor concentration, which is a P channel. So just take this extra information for your subject knowledge. Just note down up to there. So one thing after seeing these formulas, you have to understand pinch off voltage will not depend on the VGS voltage and VDS voltage. It depends on the doping concentration of your channel. How much you are doping your channel, that will decide the pinch off voltage. Okay, if you add more doping, your pinch off voltage will be more because it's a direct proportionality is there. Okay, in the theory questions they may ask you this type of questions. As the doping of your channel increases, what happens to pinch off voltage? It will be directly proportional to the doping concentration of your channel. So complete clearly up to here. So with this I have been covered. The total mechanism is also completed. N channel, P channel, total stories are completed now in the class. So what is IDSS? We know. What is pinch off voltage? These things we have been understood. We're coming to the final steps now. Concept. Finally, what is the meaning? Mathematics is important for analog. What is that mathematics we'll understand? Sumanta, you're asking why the pinch off voltage, both magnitude of VDS and VGS are equal. If you see this common sense point, if you take this as 0 volts plus 3 volts, if you add there, VGS is 0 and VB is 3. Suppose if you have thrown there, 0 plus 3 is 3 only or not? Okay? And here minus 3 is there, at the time your VDS is 0 volts. Okay? Minus 3, if you throw, it will become 3. VDS is 0, 3 plus 3, 3 plus 0 is 3 on. So whatever you do, whatever the voltages you change, it should become 3 value. That means if VDS becomes 1, pinch off voltage is 3 suppose, then automatically VGS will be 2. Like that we can calculate the values. Afterwards you can apply the signs. Okay? If you want for VGS, sign will be negative. If you want VDS side, the pinch off voltage will be positive. Like that you can explain. Generally, we don't want a positive sign, we want negative sign because ID will be 0 at what place, it will decide the pinch off technique. So that's why here is more interesting rather than here. Because this information already will be given by the examiner. At 3 volts, how much maximum current is explained. So there is no importance of plus 3, there is importance of minus 3. Shabnita's pinch off voltage will never be always positive. It's only modulus to understand how much is the pinch off voltage for it. Okay? Pinch off voltage, already examiner has given this. Only to find out any voltage, any one parameter, we have this equation with us. Okay? VGS and VDS, suppose you want to find in your problem, that relation will help you to calculate the technique, pinch off value. Otherwise we can solve the VDS and VGS. Again, net is talking. The arrange straightforward will keep. I prepare chairman, just by tomorrow. This net problem daily is coming. Huh? Students, okay, but I have to see now, laptop. So please complete up to here. So if it is completed, please just message me so that we'll come to the final story today. That is how to write the transfer characteristic equation of JFET is more important for analog classes. That means what is the relation between ID to VGS? We are interested now. Okay, that is called transfer characteristic equation. We have to add to both the batteries to run the JFET. Let's show it differently. Both the batteries we have to work. Okay, one should not be maximum, one should not be minimum. We should not work on that. We have to take both the batteries and we have to work under the pinch off conditions. Shabnita's here doping concentration importance going here. If you add more and more doping, okay, your pinch off voltage will increase more and more. But this person is telling pinch off voltage should not be more, it should be less is important. If the pinch off goes more and more like this, to make on and off switching, it will take more time for you. If you want to have a less switching and a faster switching speed, the pinch off voltage should be less values. That's why in electronics, the N channel what you created is likely doped we have taken. Whenever N channel is likely doped, automatically your pinch off will be less values. We don't want more values, pinch off, we want less values. Okay? We want less values, pinch off voltage. Let us start completing the final story. So keep the heading, transfer characteristic equation. Keep the heading, transfer characteristic equation. It's a very important equation. Transfer characteristic equation of JFET. Very, very interesting equation. One of the best equation I can say in JFET devices. ID is equal to IDSS into 1 minus VGS divided by VB whole square. This is the standard equation of JFET. So we should not forget these equations because the total analog game will be with the simple equation. So ID is equal to IDSS into 1 minus VGS by VB whole square. So what it is defining is your transfer characteristic graph it is deciding. You have seen the graph is looking like a parabola. It's decreasing like a parabola because it's a parabola equation there. So IDSS into, okay, thank you Aditya, thank you very much. So IDSS into 1 minus VGS by VB whole square. This equation is valid. It is valid for N channel also. It is valid for N channel and P channel also. This formula is valid for both N channel and P channel JFET. For both we can use it. Okay. Now the second point is very important is from this parameter how to calculate the transconductance, one important concept, which is a very valuable parameter for amplifier concepts. I'm introducing a term called GM, transconductance we call in electronics. So how to get transconductance? First of all, in BJT, how to get the transconductance I'll show you. Then I'll come to JFET transconductance because throughout the amplifiers, GMs are very important. Transconductance is a strength for the amplifier. Then how to calculate, at least you must know what is the GM formula for the BJTs and what is the formula for JFETs. So first we'll go for BJT concept. In BJT, if you see the concept, BJT concept, your IC current formula is IS into e power VBE divided by eta VD. This is the IC current relation we have. Okay, this is the IC current relation. So if you know this is our IC current relation, if I want to differentiate output current to input voltage, if I want to differentiate your IC current in terms of VBE, then we call it as GM in the class. GM is nothing but expression of this value. You can see here, differentiate with respect to VBE. Suppose if I do in the concept, it will become derivative of IC by derivative of VBE, which we are calling this as GM in the class. That means output current change with respect to the input voltage change, we call it as transconductance. Okay, output current change by input voltage change, we call it as transconductance. In BJT, this is your diode current equation. Just I am differentiating with respect to VBE. Then the answer will be IS into e power VBE divided by eta VT divided by just VB derivative is eta VT. So this is the way you are getting GM value. Okay, so this equation can be written as GM is equal to, it is IC divided by eta VT. So this is called GM in the class. This is called BJT GMs now onwards in electronics. So in future yellow classes, don't keep surprising faces, okay? When I'm teaching the design part, GMs will be normal for me in the classes. GM always depends on your operating current, which is your DC current. So from biasing circuit, you have to calculate the operating current called ICQ. Then only GMs we can find out in amplifier circuits. Okay? Why I said biasing is most important in my life is, without calculating ICQ current from the biasing circuit, we cannot get GMs. If you don't get GM, EV, voltage gain is proportional to GM will come in the next class. If GM if you know, you can find the voltage gain immediately. That's why indirectly, the DC analysis will help you a lot. DC analysis will help you a lot. So GM always depends on biasing circuits. DC biasing circuits. This is very important is GMs will come from biasing circuits. Okay? So what about the story about field effect transistor called J effect? Now if anybody asks me J effect knowledge, J effect wise what is GM? Then we have an equation here. ID is equal to IDSS into 1 minus VGS by VB whole square. This is my transfer characteristic equation thing. This is the transfer characteristic equation BJT class. This is the transfer characteristic equation FET class. It's an exponential, that is a parabola. Okay, both the dimensions are different. Panja, if you want to know what is the physical significance of transconductance, transconductance is the strength of the device, is the physical strength. Okay, how much it is getting amplified, voltage gain, how much it is getting amplified will come from the strength of GMs, transconductances. Okay, that's why transconductance physical meaning is the strength of the devices we call. Amplifier strength will be measured by GMs. So differentiate with respect to VGS you do it. Okay, it will just decide the strength of the device, amplifier strength. If your GM is very less, if you say in electronics, your amplifier strength is very less. If your GM is very high, your amplifier strength is very good. Like that you can measure the strength of the device. That is called GMs. So if I take differentiation of ID by differentiation of VGS, which is called GM again, change in the output current by change in the input voltage, it will be minus 2 IDSS divided by VP into 1 minus VGS divided by VP. So this is the way you can write. So it just x square derivative I have done here, nothing else. X square derivative I have done 2x, and VGS is 1 derivative, so 1 by VP will come out with minus 1. So this is about GM. This is about GM formula. And VGS is nothing but your operating voltage. That's why biasing classes are important. If you don't know biasing classes, we cannot find out the VGS to operating voltage. If you don't get operating voltage, we cannot find out the GMs. That's why indirectly, this also depends on DC biasing circuit. So that's why biasing circuits are very, very valuable for us. BJT biasing, we got all the biasing circuit knowledge. Like that today, we have to play the role for FET biasing knowledge. Each biasing, how to do it, that logic you have to understand, so that we'll be perfect in doing the amplifier design questions. Okay? This is the main secret why biasings are required. Why biasings are very important for our life. Minus 2 IDSS divided by VP into 1 minus VGS divided by VP. Okay. So this completes the story of GM. Suppose if anybody asks you maximum transconductance, when you will get in J effect, there's a concept here. Maximum transconductance. Maximum transconductance, which is indicated by letter GMO. If anybody is asking you, please tell me what is the maximum transconductance in J effect. What to do is, I think here VGS Q, whatever you have seen, your operating voltage should be kept at 0 volts. Because in J effect, when VGS becomes 0 volts, you will get the maximum channel. Correct? If you get a maximum channel, you will get a maximum GM. Therefore, the answer will be simply minus 2 IDSS divided by VB. This is the maximum strength in your J effect at VGS equal to 0 volts. This is the maximum strength we call. We call it as GMO, indication for it, maximum transconductance in electronics. So friends, I think with this I've been completed successfully. The first topic I completed today in device part called J effect electronics is completed. Next my job is MOSFET user. So I'm expecting we'll take some 15 minutes break, okay? So that we'll refresh and we'll start the MOSFET. The next instant MOSFET will be completed. After that we'll have a lunch break. Lunch break we'll try to see the testing part, and biasing part is the final analysis part. Okay? These two modules will complete. So I'm expecting now electrical students, I feel that you got an idea about this device. Okay? In a lucid manner I'm teaching the concepts without increasing the level of each and every point, expanding electric-based concepts I'm explaining for you. Because we don't want in-depth knowledge about devices. We want a concept how to apply to the analog electronics is very important for electrical students, mainly for electrical students. So anyway, all the points have been covered. Nearly all the points are covered. So let us have a break for 15 minutes and we'll start a MOSFET class now, MOSFET device analysis. So take a break for 15 minutes now. It is around 11:35. So we'll go for 11:50, we'll start the class. Take a break up to 11:50. Just for 15 minutes break. 15 minutes, please take a break. We'll continue after the break. Okay? Thank you, Tripti Roy. Thank you very much. If you understood means I'm so happy for that. My efforts are going in good manner. Great. So take a break for 15 minutes. After 15 minutes, we'll start the class. So have a relief for 15 minutes. Yeah, Sandesh. Thank you very much. Thank you.